This is SpaceTime, Series 25, Episode 110. Coming up on SpaceTime, scientists change the orbit of a celestial object for the first time in history. Astronomers have just detected a record-breaking gamma-ray burst. And NASA's planet-hunting TESS spacecraft placed into safe mode following a sudden computer glitch. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have altered the orbit of a celestial object for the first time in history. Observations using an array of ground and space-based telescopes have confirmed that the impact of NASA's DART spacecraft into the asteroid Dimorphos successfully changed the 160-metre-wide moonlet's orbit around its host asteroid Didymos. Prior to the collision, Dimorphos took 11 hours and 55 minutes to complete one orbit around the 780-metre-wide Didymos. But following DART's impact, Dimorphos' orbit around Didymos was cut by some 32 minutes, shortening it down to 11 hours and 23 minutes. Astronomers say this measurement has a margin of uncertainty of approximately plus or minus 2 minutes, but it still far exceeds the 1% or 10 minutes scientists were hoping for. Before its encounter, NASA defined a minimum successful orbital period change around Didymos of 73 seconds or greater. But the early data suggests DART surpassed that minimum benchmark by more than 25 times. This marks humanity's first time purposely changing the motion of a celestial body, and the first full-scale demonstration of asteroid deflection technology. DART took 9 months to travel the 11 million kilometres to rendezvous with its target. NASA Administrator Bill Nelson says the mission is a watershed moment in planetary defence and shows how NASA's trying to protect the Earth from whatever the universe throws at us. Meanwhile, the director of NASA's Planetary Science Division, Laurie Glaze, described the result as an important step towards understanding the full effect of DART's impact with its target asteroid. Now, as the new data comes in day by day, astronomers will be able to better understand and assess whether and how a mission like DART could be used in the future to help protect planet Earth from a collision with a large asteroid heading directly towards us. The investigative team is still acquiring data from ground-based observations around the world. They're updating the periodicity measurements with frequent observations in order to improve its precision. Focus now is shifted towards measuring the efficiency of momentum transfer from DART's roughly 22,530 km/h collision with its target. This includes further analysis of the ejector, the many tons of asteroidal rock displaced and launched into space by the impact. Turns out the recoil from this blast debris has substantially enhanced DART's push against Dimorphos. It's acting a little bit like a jet of air streaming out of a balloon, sending the balloon in the opposite direction. To successfully understand the effect of this recoil from the ejector, more information on the asteroid's physical properties, such as the characteristics of its surface and how strong or weak it is, will be needed. These issues are still being investigated. Astronomers will continue studying imagery of Dimorphos from DART's terminal approach, and from the Italian Space Agency's Lycia Cube, the light Italian CubeSat for imaging of asteroids. This will help approximate the asteroid's mass and shape. Roughly 4 years from now, the European Space Agency's Hera mission is also planned to conduct detailed surveys of both Dimorphos and Didymos, with a special focus on the crater left by DART's collision and a precise measurement of Dimorphos' mass. Professor Stephen Tingay from Curtin University says that by any measure, the DART mission has been a tremendous success. The idea of deflecting an asteroid for planetary defence has been around for a long time, and it's even inspired numerous science fiction disaster movies. But now the engineering and science have caught up. Tingay says if in the future an asteroid's found to be on a collision course with the Earth and astronomers have enough warning, a next-generation mission based on that experience could well save the Earth and humanity from significant losses.
Pretty ambitious mission run by NASA with the involvement of the Italian Space Agency. They launched the mission, the spacecraft, back in November. The object of the mission was to collide the spacecraft with an asteroid in an attempt to change its trajectory, and this was the very first test of planetary defense techniques. That is, what you see in the movies, redirect an asteroid so that it doesn't hit the Earth. So this asteroid had no chance of coming anywhere near the Earth, but it was a test of the technique so that in the future, if there was some chance of an asteroid impact, we basically now have proven techniques to attempt to avoid that. The orbit was changed. It was changed by sort of 32 minutes, which is an enormous change. So well above the thresholds for success and, a really spectacular demonstration of the technique. There was a lot of uncertainty as to what the result of the impact would be because it depends on all of those uncertain factors. So, exactly where the spacecraft hits, how hard it hits, and really uncertain the composition of the asteroid itself and how the asteroid would react to the impact. So that the test that's been undertaken is going to provide an enormous amount of information on those characteristics, which is really going to help provide detailed planning and detailed scenarios for if we ever had to do this for real.
The ejector plume's a lot larger than a lot of people were expecting. That must be telling us something about the internal structure of Dimorphos. Obviously, much more of a dust pile or a rock pile asteroid than a solid rock.
What really surprised me about the immediate aftermath of the collision was just how spectacular the debris plume, the cloud of material that was ejected from the collision was. I'm not sure what I was exactly expecting, but I was amazed that even small telescopes from Earth could observe and pick up the enormous plume of debris that was produced by the impact. It was absolutely astonishing. There are some incredible videos from relatively small telescopes that observed the event. That was an enormous cloud of debris that was ejected, and it actually ended up acting a bit like a gun that has a recoil. So the ejector were thrown out in one direction, and that actually, the conservation of momentum means that the asteroid itself goes in the other direction. So that was, I guess, from my point of view, a little bit unexpected, and it does show that this particular asteroid and probably many asteroids are a fairly loosely aggregated small rocks and large rocks and dust and pretty loosely held together. That debris cloud has evolved into a quite long tail that is now following the asteroid through the solar system.
This is an asteroid pair which isn't a threat to Earth right now, but they still are near-Earth asteroids, and they've got lots of friends out there as well. I think the latest count is, 30,000 near-Earth asteroids?
There are a lot of asteroids, and they vary in size and therefore would vary in their impact if they ever hit the Earth. Happily, the types of asteroids that would really challenge the existence of civilization if they hit Earth, they're sort of in the 1,000 metre plus diameter range. And there's something less than 1,000 of those sized objects, and happily we know about 95% of them in a lot of detail already. There's 5% probably that we have not yet identified or catalogued, and maybe it's those that pose the biggest risk. At the smaller end of the size scale, there's a huge number of objects that could impact the Earth in the tens of metres category, not life-threatening for Earth, but would cause a bit of a mess if they occurred over a populated area. We probably only have catalogued about 30% of those types of objects, roughly speaking. So there are a lot of risks out there, but most of them are relatively minor risks. Happily, we understand pretty well the really big objects in the asteroid class.
Nevertheless, every month I do a report somewhere, either on radio or in the show, about an asteroid that astronomers have just noticed after it swept past. Obviously, a lot of these are ones coming from the direction of the sun.
The type of impact that could really threaten civilization come around with a spacing of hundreds of thousands of years. So there's no immediate threat. And what astronomers call a close call, the normal person in the street probably wouldn't call a close call. If something comes closer than the moon, we tend to get a little bit excited. It's still a long way away. And generally speaking, these are relatively small objects. So no, it's not something that keeps me awake at night. Maybe I sleep 1% better these days knowing that a mission like DART was successful.
Do we need a proper Space Watch type of operation for the Southern Hemisphere? There's a very good one in the Northern Hemisphere, but nothing south of the equator.
Well, there have been some fairly substantial programs in the past that have operated from the Southern Hemisphere, and there is still some activity, but obviously there's a bigger concentration of land mass and resources in the Northern Hemisphere. So I would say yes, we probably do need more of that planetary defence surveillance from the south. I think we could do more of it all over the planet, actually. And it's not like these facilities are really all that massively expensive. Even with a relatively small telescope, some pretty effective surveillance can be done. So a worldwide network of small but capable facilities could go a long way.
That's Professor Stephen Tingay from Curtin University. And this is SpaceTime. Still to come, astronomers have just detected a massive record-breaking gamma-ray burst. And NASA's planet-hunting TESS spacecraft has been placed into safe mode following a sudden computer glitch. All that and more still to come on SpaceTime. Astronomers have just detected a record-breaking gamma-ray burst. The event, which reached Earth on October the 9th, has been catalogued as GRB 221009A. It was initially detected in X-rays, picked up by NASA's Swift Gamma-Ray Space Telescope. Then other telescopes began focusing in on the source of the blast. It was so powerful that astronomers originally thought it must have occurred fairly nearby. However, follow-up observations showed that it actually originated in a dusty galaxy more than 2.4 billion light-years away. The burst was so bright, it's now believed to have been the most energetic gamma-ray burst ever detected, with up to 18 tera-electron volts. Gemma Anderson from Curtin University's node of the International Centre for Radio Astronomy Research says while its closeness makes it appear to be brighter than it really is, it's still possibly the most intrinsically bright gamma-ray burst ever seen. Astronomers are now training their telescopes on the burst's location to study the evolution of this blast and its afterglow across as many electromagnetic wavelengths as possible in order to better understand the event. Gamma-ray bursts are the most powerful explosions in the universe since the Big Bang 13.82 billion years ago. These blasts release as much energy in a few seconds as the Sun will produce in 10 billion years. Short-period gamma-ray bursts, which are less than around 2 seconds, make up roughly 30% of all gamma-ray bursts, are hypothesized to be produced by the merger of two neutron stars in a close binary system. As they crash into each other, they produce a kilonova and transform into a stellar mass black hole. Long-period gamma-ray bursts, usually lasting more than about 2 seconds, make up the other 70% of all gamma-ray bursts. They're hypothesized to be generated by the core collapse death of the universe's largest stars, in what are termed a hypernova or a superluminous supernova. These either mark the birth of a stellar mass black hole or a highly magnetized neutron star called a magnetar. This is SpaceTime. Still to come, NASA's planet-hunting TESS spacecraft placed into safe mode following a computer glitch, Rocket Lab sets a new launch record, and later in the science report, researchers in Melbourne have taught a dish of living human and mouse brain cells to play Pong. All that and more still to come on SpaceTime. NASA's planet-hunting TESS spacecraft has been placed into safe mode following a sudden computer glitch. Mission managers say TESS unexpectedly went into safe mode, halting its observations following a reset of the spacecraft's flight computer. They say the probe is stable, and observations yet to be transmitted to Earth appear to be safe. TESS circles the Earth in a highly elongated orbit, relaying data only when nearest to the Earth. The Transiting Exoplanet Survey Satellite, or TESS mission, was launched in 2018 as a follow-up to the Kepler spacecraft hunting for planets orbiting stars beyond our solar system. TESS searches for planets using the transit method, looking for a regular dip in light coming from a star, that dip possibly being caused by a planet passing or transiting in front of that star as seen from TESS's position in space. Originally designed to operate for 2 years, TESS has continued to survey the skies, identifying over 250 confirmed exoplanets and detecting thousands of candidate worlds, all adding to science's now 5,000-strong list of exoplanets. Rocket Lab has broken its annual launch record, carrying out its 8th mission this year. The company's previous record was set in 2020 when it undertook 7 launches in a single calendar year. The It Goes Up From Here night launch saw the Electron rocket blast into the sky from Pad B at Launch Complex 1 on the Mahia Peninsula of New Zealand's North Island east coast. The mission was Rocket Lab's 31st Electron launch overall, with the company having undertaken a launch every month since April. The It Goes Up From Here mission for General Atomics Electromagnetic Systems carried the Gazelle satellite loaded with the Argos 4 Advanced Data Collection payload. That's an international Earth observation collaboration payload between several United States government departments, including NOAA, the National Oceanographic and Atmospheric Administration, NASA, and the French space agency, TESS.
Okay, all stations, we are go for out of sequence start. LD is go for launch. LD Shadow, confirm go for launch.
Confirm go for launch.
Vehicles on internal power. AFTS is green and enabled for flight.
LOX load complete. LOX system in research. All helium anti-gas ring disabled.
Stage 1, Stage 2, press for flight.
High flow engine purge enabled. Deluge activated.
10, 9, 8, 7, 6, 5, 4, 3,
Ignition.
2, 1, liftoff.
Stage 1 proportional, nominal.
T plus 38 seconds and our 31st Electron has lifted off from the pad at Rocket Lab Launch Complex 1. Electron is powering its way to orbit for General Atomics. The next milestone after liftoff is max Q, or maximum aerodynamic pressure. This is the moment during launch when the forces on Electron are at their peak, causing the most amount of stress on the rocket.
Clear max Q.
HV battery discharge nominal.
That's confirmation from Mission Control. Electron has successfully throttled down, passed through max Q, and ramped back up ahead of stage separation. We're currently traveling at over 2,000 kilometers per hour and at an altitude of over 20 kilometers. The next 3 milestones happen in relatively quick succession, within seconds of each other. First things first is MECO, or main engine cutoff. The 9 Rutherford engines will throttle down and then shut down completely before step 2 of this sequence. Separation of the first and second stages is next. The first stage drop away from the stage 2 body. And lastly, to continue our journey to orbital insertion, we'll see ignition of the single Rutherford engine on Electron's second stage, continuing the journey to deliver the Gazelle spacecraft to its destination.
MECO confirm.
Stage separation successful.
Stage 2 ignition.
We've had successful MECO, separation, and stage 2 ignition. Now that we've passed through the harshest part of Earth's atmosphere, we no longer need to protect the payloads, so we can eject the fairing halves to save some mass. Fairing has successfully ejected. Stage 2 is continuing nominally with its General Atomics payload to orbit. The vehicle is currently at over 120 kilometers of altitude and reaching speeds of more than 8,500 kilometers per hour.
Guidance is nominal.
Stage 2 propulsion is nominal.
Everything is looking great at the start of our stage 2 burn. Electron powers through space at over 9,000 kilometers per hour. Those propellant levels depleting slowly, with about 76% of liquid oxygen and 75% of RP1 kerosene remaining. Those familiar with our 3D printed engines will know that Rutherford engines use batteries to power their propellant pump. But, much like anything that runs on batteries, that power source gets depleted, and soon a fresh battery is required to keep things going. The process of switching out this power source mid-flight is what we call the battery hot swap.
Stage 2 propulsion still nominal.
Hot swap successful.
And battery hot swap is confirmed, where we switched out the depleted batteries from feeding the Rutherford pumps on the second stage engine with a new one. The pumps are driven by an electric motor which provides fuel and oxidizer to the combustion chamber, spinning at a rate of over 42,000 RPM. The Stage 2 engine is powering the General Atomics payload to its destination orbit at 750 kilometers above Earth at an inclination of 98 degrees, the Sun Synchronous Orbit, or SSO. This allows the satellite to be positioned over the same location on Earth at the same solar time every day. We're well above the Kármán line now and on our way to orbit. The vehicle with payload is healthy, currently traveling at speeds of over 18,000 kilometers per hour and at an altitude of over 290 kilometers. Our first mission from LC-2 in Wallops, Virginia is slated for the end of this year, and we're all very excited to baptize our third launch pad in fire from those 9 Rutherford engines. A quick update from Mission Control for our 31st Electron mission. It all goes up from here. Electron is cruising at a speed of over 22,000 kilometers per hour, and it's in an altitude of just over 300 kilometers. With just a 10% LOX remaining and 10% RP1 remaining, we're coming up on SECO or second engine cutoff ahead of kick stage separation.
Guidance on tonal, 27 seconds remaining.
SECO confirm.
Nominal transfer orbit.
Stage 3 separation confirmed.
Much like main engine cutoff, the Stage 2 Rutherford has now throttled down before the stage separates from the kick stage as it continues on to payload deployment in the next 40 minutes or so. Stage 2 and the kick stage now have separated. The kick stage will now enter what we call a coast phase. For the next 45 minutes or so, the kick stage will be in an elliptical orbit around Earth before the Curie engine ignites and raises the kick stage's perigee to put us in a circular sun-synchronous orbit. From here, we'll deploy General Atomics' Gazelle satellite.
Argos 4 joins a network of other Argos payloads now in orbit designed to collect data to provide scientists with a better understanding of Earth's physical and biological environment. This includes the planet's weather and climate, its biodiversity and ecosystems, as well as assist with maritime security, offshore pollution, and humanitarian assistance. Rocket Lab remains on track to continue its monthly launch cadence for the rest of the year, with missions scheduled to continue to launch from New Zealand, as well as the inaugural mission from the new Launch Complex 2 at NASA's Wallops Island Flight Facility on the Virginian mid-Atlantic coast. This is Space Time. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.